Go. Good morning, everybody. Welcome back to Abstract Algebra. Plan for today is to kind of finish our discussion of our introductory group worksheet, and then continue on to talking about a special type of group called a dihedral group. Make sure that you have a copy of the new worksheet, the dihedral group worksheet, as well as a little baggie with shapes in it. We'll be using that here in a little bit. Next talk starts are going to be on Monday, the hour before class, and from 1 to 2, which you'll be able to sign up for over the weekend. And homework 1 has been written but not posted yet, but it will be posted this afternoon on Blackboard. I'll let you know when and where that is. And homework 1 is going to be due next Friday. Yes?
Will it just be over the first 2 classes?
Mainly just over like the first class and a half worth of stuff. Yeah. So homework 1, just so you know, is going to be a bunch of examples of here are some sets along with some binary operations. Which one of these form groups? And if it does form a group, what's the identity? How do inverses work? If it's not a group, what goes wrong? Which of the 4 conditions for having a group doesn't fail? And so this homework's mainly going to be designed to kind of introduce you to a bunch of the different examples that we're going to be looking at over the course of the semester, as well as giving you some practice and being able to identify what makes a group and what does not make a group. I remembered to hit record, to bring my computer and hit record this time. I'm proud of myself. Any questions or comments before we get started today? What's that, Lauren?
I have a real question and then my regular question.
Okay. What do you want to do first?
Are you going to send something out or post something on how to get latex?
Yep. Planning on doing that this weekend.
Okay, thank you, because I tried to find it and I was just confused. And then, you got any books?
Absolutely. What did 0 say to the number 8?
Twice the man I'll ever be.
Twice the man. You're infinitely times the man I'll ever be. Oh, okay. Alternatively, nice belt. Okay. So last time we had introduced this idea of what does it mean to make a mathematical group. We said that it's groups made up of a set of objects and a binary operation, star, where the binary operation is just some way of taking 2 elements in the group and producing a single element. And we said that these 2 things have to satisfy the closure property, meaning given any 2 elements from your set G, potentially the same element twice, you have to be able to take A star B and always get back something within the set G. We have to have associativity, meaning you can play with parentheses when you do multiply 3 things, or star 3 things together. A star B star C is the same as A star B star C. We needed to have some identity element, something that if you take anything in the group star the identity, or that identity star anything else in the group, you'll get back that other thing in the group. Meaning something in the group that if you star with on either side, nothing changes. And finally, we need to have inverses. Meaning given any element in the group, we need to have something that we can star with it that'll get us back the identity element. Last time we looked at the integers as an example in which we proved that the integers did form a group under addition, where our identity element was just the number 0, and inverses were made by taking negatives. The inverse of 2 was negative 2. If you added 2 to negative 2, you got 0, for instance. And we said that the integers did not form a group under multiplication, because while it had this closure property, an associativity, and an identity, namely 1, if you multiply by 1, nothing changes, we did not have inverses, meaning for most integers, you can't find any other integer to multiply by that'll give you back 1. And so I wanted to start off today by looking at a slightly more interesting example of a group. And I want to talk about GL2R. So here I'm going to be on page 3 of the worksheet packet from last time. Out of curiosity, has anyone seen this notation before? GL2R? Peter? Oh, yes.
All those 2 by 2 matrices with real numbers is the component.
Yeah, it's going to be 2 by 2 real matrices. This is going to be defined to be the set of all 2 by 2 matrices all 2 by 2 matrices that have some property to them.
Right. Real numbers.
2 by 2 matrices with real number entries. Turns out there's one more property that we're going to have for matrices in here.
Do they need to be invertible?
They're going to be invertible 2 by 2 matrices. So in other words, matrices that have an inverse, which, given that linear algebra is a prereq for this course, I'm hoping that you've seen at some point. But basically, if we want, we can write that out using SetBuilder notation by kind of putting set brackets around it. It's the set of all matrices that look like this, that are 2 by 2, so 4 different letters here, satisfying that A, B, C, and D are all going to lie in the set of real numbers. They're all going to be elements of fancy R. Fancy R just means set of all real numbers. And if we're looking at a 2 by 2 matrix like this, what condition does it need to satisfy in order to be invertible? Kind of several different ways we can kind of say how a 2 by 2 matrix like this is invertible, but
What was it? AD minus BC equals 0.
AD minus BC is not 0.
Not
Yes.
0.
Yeah. Yeah. So in linear algebra, you probably had a theorem that was like the following are equivalent to a matrix being invertible, and you probably had like 30 different equivalent conditions to it. Like the rows are linearly independent. The rows span R2. The determinant is non-zero. Is a kind of a quick way of saying a matrix is invertible, which for a 2 by 2 is the same as just saying that AD minus BC is non-zero. Because AD minus BC is the determinant of this arbitrary 2 by 2 matrix. So you may have noticed I kind of used some fancy set brackets kind of around this whole expression. This is something that we'll see throughout the course called SetBuilder Notation. And what it means is just, if you want to define a set of objects, you're first saying it's the set of all things that look like this. Like this is what the elements in our set are going to look like. And here are the conditions the individual pieces need to satisfy, kind of after the colon. So we're saying A, B, C, D all need to be real numbers. And that's kind of where this fancy R is coming from. Basically saying we're allowing the elements, the entries in our matrix, to be any real number you like. So you could have pi, e, 27, negative square root of pi over 17. But you can't have any imaginary numbers, no i's showing up in our matrices here. And we also want to satisfy the condition that A has non-zero determinant, i.e. that AD minus BC is not equal to 0, and that's so that we get that all of our matrices are invertible. So what I would like to do is I would like to check, is GL2R a group under multiplication, and is GL2R a group under addition? Which one would y'all like to start with?
Addition.
Addition. All right. Let's check GL2R under addition. Okay, so first of all, let's start with the question of closure. So if we have two matrices, if A and B are going to be 2 by 2 invertible matrices, must A plus B lie in GL2R as well?
think so.
You don't think so? Can you give me a counterexample, please?
Yeah, I don't know, just create specific numbers. If you had, I just imagine there's a way to add two matrices so that neither of them have a determinant of 0 at the beginning, and you could.
But their sum does have a determinant of 0?
Right, is that, I mean, I would have to create a specific counterexample, but that seems doable.
Okay, let's see if we can do that. Can we come up with two specific matrices whose sum, where each of the two matrices themselves are invertible, but their sum is not invertible? Okay.
Could you just take like A and negative A, so that your entries become all zeros?
Cool, give me an A.
So 1, 2, 3, 4, I don't know if that'll be invertible, but hopefully it is.
Let's see, the determinant is 1 times 4 minus 3 times 2, that's going to be negative 2. So A is in GL2R, since the determinant is negative 2. And B, you want to just be its negative? Sure. So B, we can just let be negative 1, negative 2, negative 3, negative 4. So that's going to have a determinant of 4 minus 6 is negative 2. Because negative 1 times negative 4 is a positive 4. And we'll subtract off negative 3 times negative 2 is positive 6. A plus B is going to give us the 0 matrix. 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0, 4 minus 4 is 0. We add the entries. And is the 0 matrix an invertible matrix? Well, if we take the determinant of A plus B, we're going to get 0 times 0 minus 0 times 0. Oops. Then A plus B is not in GL2R. Murphy used all the good chalk pieces. Uh-oh, SpaghettiOs. We found two matrices, A and B, each of which lie in GL2R. Their sum does not lie in GL2R since it's not an invertible matrix. What does that tell us?
Not a group.
It tells us we do not have closure, and therefore we do not have a group. So we can say that since sum A and B in GL2R satisfy that their sum is not in GL2R, we do not have closure, and thus no. Because all that it takes in order for something to not be a group is something is not a group if it doesn't satisfy any one of these four properties. And all that it takes to not satisfy one of these four properties is we can find a single example where it fails. If it did have closure, we'd have to show that closure works no matter which matrices we started with. We'd have to be able to show that an arbitrary A and B in GL2R satisfy that their sum is in GL2R. But to show that it doesn't work, all that we need is a single counterexample. Like this one works. 1, 2, 3, 4, and negative 1, negative 2, negative 3, negative 4 are two matrices in GL2R whose sum is not in GL2R. Therefore, we do not have closure and we do not have a group. All it takes is one counterexample to spoil the entire dish. Make sure you test your dishes carefully. Any questions about this? If we wanted to, we could go on and also check for associativity, identity, and inverses, but we don't have to. Since condition 1 fails, doesn't matter what if conditions 2 through 4 work or not, we're still guaranteed to not have a group. If condition 1 did work, we then would have to check 2 through 4 in order to be able to prove we do have a group. Any questions about what we did here? By the way, it turns out GL2R doesn't have an identity element either. Kind of the only 2x2 matrix that could be an identity element under addition would be the 0 matrix. But as we saw, the 0 matrix isn't in GL2R, so we don't have an identity element either. That would be another way to show that GL2R is not a group under addition. Questions or comments? Sorry, addition didn't work out. Let's check addition. Or addition didn't work out. Let's check multiplication. There, that's what I'm trying to say. So let's check matrix multiplication. Do we have all the 4 properties needed to have a group in order for GL2R to work out? Well, let's check closure. If A and B are both invertible 2x2 matrices, must their product be an invertible 2x2 matrix? The sum of 2 invertible matrices doesn't have to be invertible. What about the product? Turns out the product actually does have to be invertible. And a way you can prove it is, do you remember from linear algebra, you likely saw at some point the fact that if you take the determinant of a product, it's the product of the determinants, meaning the determinant of AB is equal to determinant of A times determinant of B. We can actually use that fact to help us prove that closure does work here. I claim the answer is yes, and that if A and B are in GL2R, then the determinant of A and the determinant of B are both non-zero. That comes from linear algebra fact that invertible matrix is equivalent to non-zero determinant. Well, if the determinant of A and the determinant of B are non-zero, what can we say about the determinant of A times B?
It's non-zero,
Why?
because the only way to get 0 is to multiply something by 0.
And we know that this is just going to be determinant of A times the determinant of B. Yeah. So the determinant of AB is something non-zero times something non-zero, and at least over the real numbers, since we're looking at real matrices, we know our determinants are going to be are also going to be real numbers. We're multiplying 2 non-zero real numbers together. That's going to give us something non-zero. And thus, since AB has non-zero determinant, that's enough to actually prove that AB also has to be invertible. And AB is invertible, i.e. A times B is invertible. So that it turns out, while we did not have closure, GL2R did not have closure under addition, we do have closure under multiplication. Here's kind of an outline, and we're going to spend a lot of time next week, by the way, talking about how do you write a formal proof like this. But in general, the way we write a proof is start with two things. Start with the things we'd like to show have property X. We're starting with A and B invertible. We want to show that the product of these two arbitrary things is also invertible. And so we kind of rely on properties that we've already seen or already proven in order to do that. I don't feel like proving right now that this fact right here, are we all okay with just assuming that the determinant of the product is product of the determinant? Thank you. Okay. So we have closure of matrix multiple of GL2R under multiplication. So let's check associativity. If A, B, and C are all invertible matrices, if we take AB times C, is that going to give us the same thing as A times BC? Yes. And again, I don't feel like proving it. Associativity is pretty much always the least fun thing to prove, because it's just always a pain. So I'm just going to say, I'm going to borrow a fact from linear algebra that says matrix multiplication in general is associative. And by the way, on the homework, when I make you prove things or groups, I'm never going to make you prove associativity. I will make you say something about identity elements, inverses, but associativity is such a slog. Unless I feel like it, in which case, that's because you've all pissed me off somehow. All right, let's check for identity. Is there a matrix that could serve as the identity element here?
The identity matrix?
The identity matrix? Whoa. What's that again?
1, 0, 0, 1.
Okay. We can say if E is equal to the identity matrix, 1, 0, 0, 1, then it is going to be the case that for all A in GL2R, E times A is going to give us A, which is going to give us A times E. By the way, is the identity matrix itself an invertible matrix? What is its inverse? Yeah, turns out this is its own inverse because of linear algebra facts. So it turns out that the identity matrix is going to be our identity element. Coincidence? I think not. All right. Last up is inverses. So given any A, an invertible 2 by 2 matrix, how can we find the inverse of A? How can we find something to multiply A by, in other words, that'll give us the identity matrix? Not a trick question. So if we are starting with an invertible matrix A, how can we find something to multiply A by that'll give us the identity matrix?
I mean, I forget how to do it, but I know each one has like A inverse.
Yeah, just take the matrix inverse. Yeah, I don't remember how to do it offhand either. Well, I know by 2 by 2 because I can brute force it, but just do all that fancy stuff you did back in linear algebra to find matrix inverses, and voila. That'll give you, by definition, the inverse of a matrix is the thing you need to multiply it by to get the identity matrix. And that's going to give us the inverses in our, turns out it is, a group. So I'm just going to say the matrix inverse, A inverse, will also be the group inverse since A times A inverse, by definition, is going to give us this identity element. So it turns out under multiplication, we do have closure, we do have associativity, we do have an identity element, and we have inverses. Group or poop?
Group.
It is a group, yes. So it turns out this is going to give us one. So it's kind of interesting. The integers gave us a group under addition, but not multiplication. Whereas GL2R gave us a group under multiplication, but not addition. So when you talk about if something is a group, you always have to be careful to say not only what is the set of objects you're looking at, but also what's your binary operation. In this case, are we talking about under addition or multiplication? Because the operation that you choose could determine whether or not you actually have this group structure to it. Any questions or comments about any of these examples of DL2R? So yeah, it turns out identity matrix, matrix inverses, this language that you learned in linear algebra is all just referring to the fact that GL2R does form a group under multiplication, and is kind of borrowing the group language in order to talk about just properties that you would only refer to with matrices in a linear algebra course. Fun fact, GL2R is called, as a special name, it's called the general linear group. That's where the name GL comes from, general linear. There's also something called the special linear group that you're going to get to learn about on homework 1. But yeah. Okay, and now for something completely different. So, next up we're going to be looking at this packet. That's a good bag for myself. We're going to be talking about a new group called the Dihedral Group, which is nothing like, which sort of doesn't look anything like GL2R and the integers. It's going to be a group of symmetries of triangles, squares, and regular entangles in general. Here's my challenge for you. Here's my challenge. I would like everybody to open up their bag and pull out the triangle to start with. One, two, three. So if you notice, your triangle and the square each have numbers corresponding to each of the corners. 1, 2, 3 on the front and back. Whereas whatever is like, this is a corner right here, 3 on the front. If I flip it over, it's that same corner, but turned around is going to be 3 on the back. Basically, think of this as your top corner. Here's corner 1, here's corner 2, here's corner 3. Your goal is going to be to find out how many ways you can pick your triangle off the table, rotate it around, flip it around, and put it back on the table and get a different configuration of numbers at each corner. For instance, one thing you can do, starting off with 1, 2, 3, is to pick it up off the table and put it right back down. Do nothing to it. And that'll give you one configuration of your corners. Another configuration of your corners is, let's say we pick it up, we rotate. I'm going to rotate counterclockwise 120 degrees. And now I'm going to get a configuration where 2 is in the top, 1 is in the bottom left, and 3 is in the bottom right. So that'll be another configuration of the corners. What I would like for you all to do is to find as many configurations of the corners like this as you possibly can by just picking up, rotating, flipping it over, doing whatever you want with it. And then here's the key. Once you find all of the configurations you believe you can find, I want you to find how, if this 1, 2, 3, like this, is that how I did it? Yes, it is the starting position. I would like you to find a configuration of rotations and flips and flipping it over that'll get it from the starting position to each of your other positions. So turns out you can do this with just single rotations and single flips combined together. We're going to let R refer to rotating 120 degrees counterclockwise. And S is going to be reflecting over a vertical line going down the middle. So if this is 1, this is 2, this is 3. Reflecting would take 1, 2, 3 like this to 1, 3, 2. It turns out by doing a kind of a sequence of 120 degree rotations counterclockwise and flipping it over like this, swapping the bottom 2 corners but keeping the top corner the same. Turns out by doing any combinations of R's and S's, doing different combinations of R's and S's like this, you should be able to get all of the triangle configurations that you found in the first step. Go ahead, take a couple minutes, see what you can find. Now, generally I'm a big proponent of work with your neighbor, turn to the person sitting next to you or around you and try talking with them. COVID is a thing. If you feel comfortable doing that and they feel comfortable doing that, you're certainly welcome to work with your neighbor. But if you don't, please don't. It's up to you. I will wander around the outskirts of the room. If you have any questions, raise your hand if you have any questions. You know how a clock works? Do it the opposite way.
R is rotation, S is reflection.
Unfortunately, reflection and rotation both start with an R, so we can't use an R for both, or it would get confusing.
Do you want us to write one for like the starting position, just being like set down essentially?
Can you find a sequence of rotations and reflections from the starting position that'll work?
Oh yeah, just a little superfluous.
Say what?
I said yeah, it's just a little redundant, so I didn't know what.
It is a little redundant. And there's multiple ways to do it. You could either rotate 3 times, reflect twice. Technically, it counts to do absolutely nothing. Pick it up and say, I'm going to do 0 rotations and 0 reflections.
That's what I was wondering, if you could do it like that.
You could.
Okay. Well, that's not fun.
Or you could get fancy and do like, all right, I'm going to rotate twice, then reflect, then rotate again, then reflect back. I don't know if that actually works. Something like that. This is clockwise, this is counterclockwise. So for instance, go from starting position to here, you could do with a single R. I drew an arrow on the board if you don't remember how a clock works. So that is counterclockwise.
Oh, I was looking for the other arrow.
That does, yeah, you're right. I just did it.
You want us to go from each triangle or just from the first one?
Just from the first one to each one, like this, going from the starting position to each of the, like I say,
I did, I think it's the same thing. I did rotate and move it. Or even like that. Yeah, you did. I always lift, rotate. Okay. So we just did it a couple of them differently. Let me go.
No touching.
We did touch this.
Good.
Yes. I'm sorry. Yeah. There's two with each one.
I just started 3.
So you've all had a chance to sort of think about these triangles. So other than these two, 1, 2, 3, and 2, 3, 1, are there any other, what other triangle configurations were you able to find?
One, 2 in the lower left, and then 3 in the lower right.
Cool. So how can you arrive at that when going from the starting position? What's the sequence of R's and S's that'll get you there?
I did a rotation, and then I believe I didn't diagram myself very well, but I believe then in the S, and then 3 more rotations.
Like that?
Yeah. Somewhere around there.
Did anybody have a simpler way of finding this configuration? Like this one can be, not saying you're wrong, but it is a complicated way. Seven? Yeah, I think this one, well, I already didn't have the picture. We'll take the starting and go to that configuration.
I mean, that's another way.
That's another way I could. I'm going to go find the simple. Goal's going to be to find the simplest way. Any other triangle positions? Yeah, here. Let's start from the top and go clockwise.
3, 1, oh.
Counterclockwise. God darn it. 3, 2, 1.
Like that?
Yes.
Cool. 3, 2, 1. How can we start from our original starting position and get to this 3, 2, 1? I don't remember this one. Oh, this one's complicated.
You reflected and rotated.
A single reflection, then a single rotation?
We're rotating counterclockwise, right?
Yes.
Yeah.
Let's see. So if we do a single reflection and then a single counterclockwise rotation. Yep. And yes, I know I said RS instead of SR. We're going to write these from right to left. And I'll talk about why once we actually define what the group is we're working over. So RS actually means do S, then R. Which may seem very counterintuitive, but there is a reason for it. And we'll talk about that here in a few minutes. Any other triangle configurations? Yeah.
2, 1, 3.
Like that? How did you arrive at such a thing?
I did a reflection and then 2 rotations.
Ooh, a reflection and then 2 rotations. Like that? I like it. Nice. Alternatively, you could do a single rotation followed by a reflection, and I think would also get you to the same thing. Turns out these are going to do the exact same thing on your triangle. And finally, I found one more. I guess it's the only possible configuration left. 1, 2. How could we go from our starting position and end up with this triangle? The single rotation? Or, I said, clearly, Lane, I wrote double, and I was thinking double, even though I said single. You should have interpreted that.
I know, I'm
Yes, a double rotation.
sorry, Dr. G, I'll do
See that you do. Also, a single rotation here, please. I rotated mine 28 times. Because if every 3 rotations, it's going to cancel out and get you back to the starting point. So 28 is 1 greater than a multiple of 3. The best multiple of 3, by the way, 27. So r and r to the 28. And r to the 301, if you prefer, are all going to give you the same configuration coming from the starting position. Iron, get busy.
Let's test that out.
So how can we go from the starting position to the starting position with the sequence of r's and s's?
Rotate 999 times.
That should do it. Any multiple of 3 rotations should do it. Or any multiple of 2 reflections should also do it. So we could put r to the 999. We could do s to the 5,000. We could do, if we want to keep it simple, s squared or r cubed. Or if we want to be cheeky, we could do 0 reflections and or 0 rotations, and that'll also get us there. All have fun with that? Cool. Do the same, turn the page and do the same thing with your square. I'm glad. So for the square, it's the same deal. Find as many different orientations as you can. And then, if this is your starting square, 1, 2, 3, 4, see if you can find a sequence of rotations and reflections that'll get you from your starting square to each one, except this time, R is going to be a 90-degree rotation, and S is going to be reflecting over the line going from the top left to bottom right. So counterclockwise. So R is going to be a 90-degree rotation counterclockwise. So that'll take this, for instance, to 4, 1, 2, 3, be a single R. And S is going to be reflecting over line from top left to bottom right. So in this case, that will give you, these will stay the same and these will flip-flop. That would be a single S. Yes?
I think that's on 3 hours.
Oh my gosh, I did clockwise, not counterclockwise. I don't know how a clock works either. So counterclockwise, that's going to be 2, 3, 4. Does that look right? Thanks for the catch.
Well, were you supposed to write down what would return it to its starting configuration, not what you did from the starting configuration?
Nope, we're going from what does it take to get from the starting configuration to
the new one.
To the new one. So
Gotcha.
here, if we start with this and we rotated 90 degrees counterclockwise, that would take us a single time, that would take us to here. And if we reflected this a single time, it would take us down to here. I'll give you a hint. There's more than 6, less than a million. I'll be nice and say there's more than 6, less than 10. How about that?
What? Good.
Okay, we're actually almost out of time, and I want to make a couple announcements. So here's a lot. Your homework for over the weekend, along with taking a look at homework 1 once it's posted, is try and finish kind of your up through the second page, trying to find how many different square configurations you have and what R's and S's will get you there. Just as a sneak peek, give you a little motivation for over the weekend, what we're actually going to do on Monday is we're going to talk about how R's and S's, here, these different ways of rotating and reflections are actually going to be group elements, and we're going to make a group out of all these combinations of R's and S's that we have. That's going to be our dihedral group. And it's going to have some wacky properties that the integers do not have, and the GL2R does not have. Couple quick announcements. Over the weekend, here's what you can expect from me. I'm going to post a link to my YouTube account where you can go in and see videos for the class. I'm also going to, I've written but still need to post my guide for how to, download LaTeX, how to download the typing program I'm going to recommend for typing up your homework, and sort of a quick guide to how to actually use it. And finally, I'm going to do the thing I'm going to post the homework. These will all be happening in the next day or so. These are all things that I've done but just haven't posted because I'm lazy. Have a good weekend. We'll see y'all on Monday.
No, you.
No, you. Double dog to you. Yes.
When you say second page, you mean 1, 2?
Yeah. This is this is the page where you're doing the same thing that we sort of did here, but for this one.
Yeah.
What on Sunday?
Thank you.
I would love to meet up on Sunday. When? Where? Sounds good.
Alright.
Stuff supporting that.